Welcome back to Basic Electronics. So far, we have looked at circuits with DC sources. There are many situations in which there is a sinusoidal voltage source in the circuit, and in particular, we are interested in the solution in the so-called sinusoidal steady state. In this lecture, we will first look at the meaning of the term sinusoidal steady state. We will then look at a convenient way to represent voltages and currents in that situation using a new concept called phasor. We will also look at how phasors can be used to represent R, L and C in the sinusoidal steady state. Okay, so let us begin. Let us try to understand the meaning of this term sinusoidal steady state with the help of this example. It's an RC circuit with a sinusoidal input voltage. There is a switch here which closes at t equal to 0, and initially the capacitor is uncharged. That means Vc is 0. Alright, let us begin with the circuit equation, this equation 1 here. What does it say? It says that this voltage drop plus this voltage drop must be the same as the source voltage. This voltage drop is R times the current, and the current is C dVc dt. So that is what this says here, R times C Vc prime plus Vc must be equal to Vm cos omega t for t greater than 0, that is when the switch is closed. The solution Vc of t is made up of two components, a homogeneous component indicated with this superscript h here and a particular component indicated with this superscript p. The homogeneous component VCHT satisfies the homogeneous differential equation RCVC prime plus Vc equal to 0. So we drop the source term, and that is how we get this equation. And this equation has this solution a e raised to minus t by tau with tau equal to R times C. Let us now look at the second part, the particular solution. Since the forcing function is Vm cos omega t, we can try Vcp of t equal to C1 cos omega t plus C2 sin omega t as a candidate solution. And when we substitute this in equation 1, we get this equation here. And the constants C1 and C2 can be found by equating the coefficients of sin omega t and cos omega t on the left and right sides. Alright, here is a specific example with Vm equal to 1 volts, F equal to 1 kilohertz, 2K here, 0.5 micro here for the capacitance, and then we get this Vc shown in this figure. The complete solution is a e raised to minus t by tau from the previous slide, that is the homogeneous part, plus C1 cos omega t plus C2 sin omega t. This is the particular part of the solution. Alright. Now as t tends to infinity, the exponential term becomes 0, this goes to 0, and we are left with Vc of t equal to C1 cos omega t plus C2 sin omega t, this part here. And we can observe that in this plot as well. This is our t equal to 0, that is the time when the switch closes, and in the beginning there is some exponential transient, and then finally that transient vanishes and we have the sinusoidal steady state. So this is known as the sinusoidal steady state response, since all quantities, currents and voltages in the circuit are sinusoidal in nature. And this turns out to be generally true for any circuit containing resistors, capacitors, inductors, sinusoidal voltage and current sources, dependent sources such as CC, CS, CC, Vs, etc. So any circuit containing these components behaves in a similar manner, that is, each current and voltage in the circuit becomes purely sinusoidal as t tends to infinity. So each quantity, each current and each voltage in the circuit would have this form in the sinusoidal steady state. Okay, let us continue, and now we want to introduce phasors. In the sinusoidal steady state, phasors can be used to represent currents and voltages. So let us see what a phasor is. A phasor is a complex number, that's why it is written in boldface here. It has got a magnitude of xm and an angle of theta. So that is the phasor x, and we can rewrite this as xm e raised to j theta, and it has the following interpretation in the time domain. Corresponding to the phasor x, we have a time domain quantity denoted by x of t, and the interpretation is like this: x of t is real part of this number, that is phasor x multiplied by e raised to j omega t. So let us see what that turns out to be. Our phasor is nothing but xm times e raised to j theta, that gets multiplied by e raised to j omega t. Now we can combine these two terms to get e raised to j omega t plus theta. What is e raised to j omega t plus theta? It is cos of omega t plus theta plus j sine of omega t plus theta, and we are only taking the real part of that expression, so therefore we get xm cos omega t plus theta. So that is what a phasor x corresponds to in the time domain. Let us make some more comments. Use of phasors substantially simplifies analysis of circuits in the sinusoidal steady state, and we will look at some examples of that. Note that a phasor can be written in the polar form or rectangular form. This is the polar form, xm angle theta, also called the magnitude angle form. That is the same as xm e raised to j theta, and that can be written as xm cos theta plus jxm sin theta. This is called the rectangular form. This figure shows how the polar and rectangular forms of x can be represented. This axis is the real part of x, which is a complex number. This axis is the imaginary part of x. This is our phasor. It has got a magnitude of xm and angle of theta. Alternatively, we can also write this component, which is the real component of x, and this component, which is the imaginary component of x, and that gives us the rectangular form. Alright. Now one final remark, very important. The term omega t is always implicit. So when we write a phasor, for example x here, we don't write omega t over there, but it is understood that omega t is always implicit, and that is how it comes in this time domain expression here. Let us now take a few examples to see how something can be represented in the time domain and in the frequency domain. Here is a voltage V1 of t, 3.2 cos omega t plus 30 degrees volts. We can write this in the phasor form. The magnitude is 3.2 and the angle is 30 degrees. So that is what the phasor looks like, 3.2 angle 30 degrees. We can also write that as 3.2 e raised to j pi by 6, because 30 degrees is the same as pi by 6 radians. Another example, I of t is minus 1.5 cos omega t plus 60 degrees. Now it is not quite in the form that we would like, because we have this minus sign over here. So let us rewrite this expression as 1.5 cos omega t plus pi by 3, that is 60 degrees, minus pi. This minus pi accounts for this minus sign here, and that follows from trigonometric identities. Alright, now we can combine these two terms and get omega t minus 2 pi by 3, and now we can write the corresponding phasor like that: magnitude 1.5 and angle minus 2 pi by 3. Next example, V2 of t equal to minus 0.1 cos omega t. Once again, we don't want this minus sign here, so we rewrite this expression as 0.1 cos omega t plus pi. This plus pi accounts for this minus sign over here. And note that we can either write plus pi here or we can write minus pi like we did in the last example here. Okay, now the corresponding phasor is magnitude 0.1 and angle equal to pi. Next we have I2 of t equal to 0.18 sine omega t. Now we require cos over here, not sine, so therefore let us rewrite this expression as 0.18 cos omega t minus pi by 2, and now we can write the corresponding phasor like that. I2 equal to 0.18, that is the magnitude, 0.18, angle minus pi by 2, so that is the angle. Let us take an example of the reverse transformation now. The frequency domain description is given, phasor I3, that is 1 plus J1 in amperes. Now we want to convert that into the time domain form. Now this is in the rectangular form. We first convert that into the polar form like that. So we have square root 2 angle 45 degrees, and this we can write in the time domain directly like that. So I3 of t is square root 2 cos omega t plus 45 degrees. And remember always that this omega t is implicit, so we don't write that in the phasor, but we understand that it is always there. Let us now talk about addition of phasors. First, let us consider adding two sinusoidal time domain quantities like this. V of t equal to V1 of t plus V2 of t. V1 of t is given by Vm1 cos omega t plus theta 1, and V2 of t is given by Vm2 cos omega t plus theta 2. Alright, now consider the addition of the corresponding phasors. This phasor corresponds to V1 of t, this phasor corresponds to V2 of t. So V1 therefore is Vm1 e raised to j theta 1, magnitude Vm1 and angle theta 1. V2 similarly is Vm2 e raised to j theta 2. In the time domain, this phasor V, which is V1 plus V2, corresponds to V tilde t with V tilde t equal to real part of phasor V times e raised to j omega t. As we have seen earlier, this is how a phasor can be written in the time domain. Alright. So now we substitute for V, that is Vm1 e raised to j theta 1 plus Vm2 e raised to j theta 2, like that. And now we can combine this e raised to j theta 1 and e raised to j omega t to obtain e raised to j omega t plus theta 1, and similarly e raised to j omega t plus theta 2 here. Alright, now we need to take the real part of this entire expression, and that turns out to be Vm1 cos omega t plus theta 1 plus Vm2 cos omega t plus theta 2. This in fact is the same as V of t right there. Alright, now what is the conclusion? The conclusion is that if we have two sinusoidally varying quantities such as V1 of t and V2 of t here, we can obtain their sum by either directly adding them, or we can add the corresponding phasors like here, and then from the resulting phasor V here we can obtain the time domain quantity like that. So from the last slide we can say that addition of sinusoidal quantities in the time domain can be replaced by addition of the corresponding phasors in the sinusoidal steady state. And this is very important for us because of the following point. The KCL and KVL equations, that is sigma ik of t equal to 0 at a node, that is all currents at a given node add up to 0, and sigma vk of t equal to 0 in a loop, that is all voltages as we go along a loop add up to 0. These equations amount to addition of sinusoidal quantities and can therefore be replaced by the corresponding phasor equations. What are the phasor equations? Sigma of the phasor currents equal to 0 at a node, and sigma of the phasor branch voltages is equal to 0 in a loop. Let us now introduce the concept of an impedance, starting with impedance of a resistor first. Here is a resistor in the time domain, that is the resistor current I of t, and V of t is the voltage across the resistor. Now in the frequency domain, we replace this current with phasor I and the voltage with phasor V. And now we can write phasor V equal to phasor I times something called Z, where Z is called the impedance. And let us actually show that we can do that. Let I of t be Im cos omega t plus theta. Then we have V of t equal to R times I of t, that is valid at all times, and that is equal to R times Im cos omega t plus theta after substituting for I of t from there. And we might define that as Vm cos omega t plus theta, where Vm is R times Im. Alright. Now the phasors corresponding to I of t and V of t are respectively, for I we have Im angle theta, Im is the magnitude and theta is the angle. For V we have Rim angle theta, Rim is the magnitude and theta is the angle. We have therefore the following relationship between phasor V and phasor I, that is V is equal to R times I, as simple as that. And we can see that from here, V is Rim angle theta, I is Im angle theta, so therefore V is simply R times I. And therefore the impedance of a resistor, which is defined as Z equal to V by I, is Z equal to R plus J0. From here Z is equal to R, and R is a real number, so we write that real number as R plus J0. So the impedance of a resistor is the resistance itself. Let us follow the same process now for a capacitor and find its impedance, marked as Z over here again. Okay, so let this voltage across the capacitor V of t be equal to Vm cos omega t plus theta. What is the current? Current in that direction is C dV dt, and when we differentiate this quantity we get minus C omega Vm sin omega t plus theta. And now we can use the identity cos phi plus pi by 2 is minus sin phi, and we get I of t equal to C omega Vm, these three terms here, times cos of omega t plus theta plus pi by 2, like that. In terms of phasors, phasor V is Vm angle theta, Vm is the magnitude and theta is the angle, and phasor I is omega c Vm angle theta plus pi by 2. Omega c Vm is the magnitude and theta plus pi by 2 is the angle. Alright, now we can rewrite I as I equal to omega c Vm e raised to j theta plus pi by 2, that is omega c Vm times e raised to j theta times e raised to j pi by 2, and this quantity e raised to j pi by 2 is nothing but j. So we get then j omega c times Vm e raised to j theta. Now this quantity is nothing but the phasor V, and therefore we can write I as j omega c times phasor V. In short, phasor I is equal to j omega c times phasor V. And therefore the impedance of a capacitor Z equal to V by I is Z equal to 1 over j omega c, and the admittance, which is defined as Y equal to I by V, is y equal to j omega c. Notice that we have omega here now. That means at low frequencies the impedance of a capacitor is large, and at high frequencies the impedance is small. Let us now repeat the process for an inductor. Let I of t be Im cos omega t plus theta. Then we get v of t as L di dt. We can differentiate I of t and get v of t equal to minus L omega Im times sine omega t plus theta. Now we can use the identity cos phi plus pi by 2 is equal to minus sine phi and get v of t as L omega Im times cos omega t plus theta plus pi by 2. So we have replaced this minus sine omega t plus theta by cos omega t plus theta plus pi by 2. Alright. Now in terms of phasors, we have I equal to Im angle theta. Im is the magnitude and theta is the angle, and V equal to omega Lim. Omega Lim is the magnitude, angle theta plus pi by 2, that is the angle. And V can be rewritten as V equal to omega Lim times e raised to j theta plus pi by 2, that is omega Lim e raised to j theta times e raised to j pi by 2. This is nothing but j, so that becomes j omega L times Im e raised to j theta, and this quantity is nothing but our phasor I. So finally we get phasor V equal to j omega L times phasor I. And from there the impedance of an inductor Z equal to V by I is Z equal to j omega L, and the admittance of an inductor y equal to I by V is y equal to 1 over j omega L. Notice that the inductor impedance also depends on the frequency, but it is directly proportional to the frequency. So at low frequencies the impedance is small, and at high frequencies the impedance is large. Let us now look at sources: sinusoidal current source and sinusoidal voltage source. An independent sinusoidal current source Is of t equal to Im cos omega t plus theta can be represented by the phasor Im angle theta, magnitude Im angle theta, that is simply a constant complex number. So we have this source in the time domain and the corresponding phasor in the frequency domain, and that Is a constant. Alright. And similarly, an independent sinusoidal voltage source Vs of t equal to Vm cos omega t plus theta can be represented by the phasor Vm angle theta, that is a constant complex number, like that. What about dependent sources? Dependent sources can be treated in the sinusoidal steady state in the same manner as we treated a resistor, that is by the corresponding phasor relationship. For example, let us consider a CCVS, that is current controlled voltage source. In the time domain we have V of t, that is the voltage across the CCVS, equal to R, a constant, times IC of t, where IC of t is the controlling current. Now in the frequency domain this relationship becomes V phasor equal to R times IC phasor. As simple as that. And similarly we can write relationships for the other dependent sources such as CC, CS or VC, VS, etc. In summary, we have seen what phasors are and how they can be used to represent currents and voltages in the sinusoidal steady state. We have also seen how R, L and C can be represented in the sinusoidal steady state using phasors. In the next lecture, we will extend these ideas to circuits. Until then, goodbye.